start with extended controllable canonical form. In this we will study introduction, mathematical representation of extended controllable canonical form and numerical examples. Last time what we have studied, if we are having g of s equal to b0 upon s cube plus a1 s square plus a2s plus a3, this we have convert into controllable canonical form. So, what we have done that last time, we have written x dot equals to 0 1 0 0 0 1 minus a3 minus a2 minus a1 plus 0 0 1 u y equal to, this is b naught, y equal to 1 0 0 into x. This we have done last time. So, what has happened? The b0 is constant, there is no any other term involved, or what we have done last time, the derivative of input u we have considered to be 0. But now today we have to consider the derivative of the input, that means we have to consider the elements in this numerator. Now question has come to our mind that if we add 0 or derivative of input is present, can it affect our performance of a plant? For that purpose what we will do, I will take one transfer function, say g of s is a standard transfer functions omega n square plus s square plus twice zeta omega ns plus omega n square. This is a standard second order transfer functions. You had studied this in a classical control. In this case omega n is the undamped natural frequency, zeta is the damping factor. Normally when we design any controller or when we check its response of any system, we are considering different types of zetas. Suppose if you consider zeta equals to 1, your system is critically damped, so you will get response of this nature. For example, if I will take here omega n equals to 2, so what will get this g of s, that is equals to omega n is 4 plus s square, and here zeta is 1, so what will get 2 into 1 is 4s plus 4. Now we will try to determine the response. So we will find that for this system also you will get response like this, you will get a critically damped response, there is no overshoot. But if you add 0, 0 means, let us say if added 4s plus 1 here, now transfer function it becomes 4s plus 4 upon s square plus 4s plus 4. So in this case if you added 0, and normally when we compare, we are comparing with this one, this with this, zeta is also 1. So what happens, we will not get this type of critically damped response, there may be certain overshoot or there may be change in the steady state error. Therefore, a 0 plays a very important role in our control applications. Therefore, today what we have to do, we have to derive the state space model of a plant when there are zeros as poles, both are involved. So now we write our standard transfer function which we have written last time as a numerator, as a denominator. So we write as g of s equal to bn sn plus b of n minus 1 s raised to n minus 1 plus b1s plus b naught s raised to n plus a of n minus 1 s raised to n minus 1 plus a n minus 2 s raised to n minus 2, process repeated, plus a1 s plus a naught. So in this case we will find that b0, b1 up to b1 they are the coefficient of numerator, and a0, a1, a of n minus 2, a n minus 1 they are the coefficient of the denominator. So both numerator and denominators are involved. So, last time what we have done? Last time we have taken a reduced model, that is what we have done last time. Suppose this is B and this is A. So, we have taken last time GS equals to 1 by A, and we have determined a model of this, that is a controllable canonical form of model which we have determined for 1 by A, 1 upon A. Now, here both B and A are involved. Now, how to do it? So, what happened in this case, we will use the concept which has been used earlier. That means, whatever thing we have done last time, that will take into account, and additionally we will consider the effect of these zeros or the numerator, we can say. Therefore, we will write this transfer function as, let us say here, this is 1 by A, this is B, and this is A. Now, here U of S, Y of S, because your transfer function is actually Ys by Us. So, what we have written here? We have written 1 by A B. So, here result is Ys by Us, B by A. So, what we will do here? This part we will carry it out by conventional approach, that is last time which you have seen, and here this thing we are added. So, here something we have to take here, some variable we have to assume. Therefore, what we will do? We will assume the variable as x of s. So, here we assume variable x of s. So, now this complete transfer function we can write down as Ys by Us equal to xs by Us multiplied by Ys by xs. So, if you see this will cancel, it becomes Ys by Us. So, now we will treat xs by Ys independently and Ys by x independently, and we will determine the model, that is the controllable canonical form of model when zeros are present. But if you see take nth order, sometimes it is difficult to understand. Therefore, for understanding purpose, what I am doing here? I am taking only n equals to 3. N equals to order of the plant, I will take as n equals to 3. Therefore, that this transfer function we can write down as g of s equal to Ys by Us. Now, here n is 3, so we will write b n3, so b3 s cube. See, n is 2, so 2 minus 1, n minus 1, that is 3 minus 1, b, that is b2 square, b1s plus b0, this is numerator, and your denominator is n is 3, so s cube plus n is 3 minus 1 2, so a2 square plus a1s plus a0. This is your transfer functions, and now here we write this is b and this is a, and this can final we write as, from this logic, xs by Us equal to 1 upon a and Ys by Us, sorry, Ys by xs equal to b. So, xs x of s by u of s equals to 1 by a and Ys by xs equal to b. Now, we move further. So, we will take the transfer function xs x of s by u of s equal to 1 upon s cube plus a2 square plus a1s plus a0. Now, what we have to do here? Now, what we will do? We solve these equations, we will get s cube plus x of s plus a2 square into x of s plus a1s into x of s plus a0 into x of s into u of s. See here, s cube x of s, a2 square x of s, a1 x of s, a0 x of s and u of s. Now, what we will do? We will apply inverse Laplace transform assuming initial conditions to be 0. So, we will get what we will get here, we will get x triple dot t plus a2 x double dot t plus a1 x dot t plus a0 into x of t into u of t. You see here. Now, we use the approach of getting model which we have seen last time, that is, you have to take the output as the first variable and remaining variable are the derivative of the output. Last time you have seen that we have output y, so we have taken x1 equal to y, but here we have taken the variable as x. So, last time what we have done, we have taken variable as y equals to x1. Now, here you have to take the variable as x1 is equals to x, that is the first variable. And now, what about the other variables? They are the derivatives. So, now we write this x2 equal to x dot and this x dot equals to x1 dot. Now, about the other variable, so as the order is 3, so we require 3 more variables, one more variable, that is we write this x3 equals to x double dot, that is equals to x1 double dot, and that is equals to x2 dot. Now, here we want x triple dot, therefore, what we are doing, we are taking x3 dot. Now, here x3 dot equal to x triple dot equal to x2 double dot. Now, what we will do, we have to write this equation in such a manner that all these variable we have to adjust. Now, here x triple dot here, so here x triple dot we write as x3 dot, you see that this one is right at x3 dot like this, and we will get as what we will get here, x3 triple dot equal to minus a2, and what is x double dot? X double dot is x3, so a2 x3 minus a1, there is x dot equals to x2, a1 x2 minus a0, and this is xt, that is we can get x equals to x1 plus u. Sometimes you can try t, here I have removed it, so that to get the simplified the results. Now, finally, we want its state space model. So, how you write the state space model? So, here we take the variables as x1 dot, x2 dot, x3 dot, that is equal to, what is x1 dot? X1 dot equals to x2, that is 0 1 0. So, we write it as x1 x2 x3. What is x2 dot? x2 dot equals to x3. So, we write 0 0 1, and what about this x3 dot? So, x3 dot we write as, you just see here, minus a0 minus a1 minus a2 plus 0 0 0 1 equals to u. So, we have derived this one, but without a derivation also we can write down the results. What we have done? What we do in third row, we write out, right, a0 a1 minus a2 and 0 0 1 only, simple. Now, that we have done for a state model, that is the state model is x dot equals to ax plus bu. Now, we want to write a output equation. So, last time when the numerator is 1, so what we have done, we have taken output y equals to x1, what we have done last time, y equals to x1 only, but here this is not like this, because if you see here ys by xs, so ys by xx there is a one transfer function, so that transfer function is b3s cube, b2s square, b1s, b naught. Therefore, what we do, we write, I will take this side, so ys by x of s, that is equal to b3s cube plus b2s square plus B1s plus B naught. So, now here what we do? We have to solve it. So, we will get ys equals to B3s cube into x of s, B2s square into x of s, B1x into x of s plus B0 into x of s. Now, what we do here? We can apply again inverse Laplace transform, assuming initial conditions to be 0. So, what we will write? We get y of t B3 s cube x of x, that is x triple dot t plus B2 x double dot t plus B1 x dot t plus B0 into x of t. So, we have already determined the values of x triple dot t, x double dot t, x dot t here. Now, we replace these values here. Now, we solve this equation, we will get y equal to B3 here x3 dot plus B2 x2 dot plus B1 x1 dot plus B0 x1. We can write t also, there is no problem, but as we have to complete it as early as possible, therefore, I am not removing these t terms. Okay. Now, what we do? We write here y equals to B3. Now, what is the x3 dot? x3 dot equals to a2 x3 a1 x2 a0 x1 plus u. So, we write down this equation, that is minus a2 x3 minus a1 x2 minus a0 x1 plus u plus this is B2, we can write down as what is x2 dot? Your x2 dot equals to x3 plus B1, what is x1 dot? x1 dot equals to x2 plus B0 into x1. Now, we solve these equations, and after solving, what we will get? We will get y equals to, we will get as B naught minus B3 into A naught, B1 minus B3 into A1, and afterward we will get B2 minus B3 into A2, this bracket completed, and is equals to x1, x2, x3 plus B3 into u. So, after solving this, we got this result. So, you will find that in this output both the elements of numerator and denominator are involved. So, as we know, B0, B1, B2, these are the terms of the numerator, and A0, A1, A2, they are the terms of the denominator. So, both things are involved, whereas earlier only y equals to 1 0 0 is been involved. But assume that your transfer function is strictly proper, because if you see earlier we have taken s raised to n, s raised to n, that is, this transfer function is a proper transfer function. But if the degree of numerator is lesser than the degree of denominator, that transfer function is called strictly proper transfer function, and for control application we always preferred strictly proper transfer function. If a transfer function is strictly proper transfer function, what we will take? The degree of numerator, we take degree of numerator equals to 2, and degree of denominator equals to 3. This is numerator and denominator. So, what will happen? In this case, this Bn, so Bn here n is 3, so B3 is 0, that means y equals to B0, B1, B2, x1, x2, x3. So, we will find that when the transfer function involves no numerator, or sorry, we can say that when the transfer function is a strictly proper transfer function, in that case output it depends on only the numerator terms, whereas when transfer function is not strictly proper, or we can say only proper transfer function, you will find that the involvement of the denominator elements. So that is the difference between the strictly proper transfer function and a proper transfer function. Therefore, as far as the performance is concerned, therefore in that case we cannot get the desired performance if your given system is a proper transfer function. We always preferred a strictly proper transfer function. Now we take one example and we will try to get the result. Okay, prior to this one, whatever we have studied, we will again see it. So here we will find this is transfer function, this is taken 1 by b, this is y by us we have taken, then here x is by us, then y is by xs we have taken, and then this is we have solved. Then we have got state space model x dot equals to x plus bu, then we take this ys, then we got y of t and this y, and this is the final model. So these things will be definitely helpful to you. Prior to this one, what we will do, we will develop a model or a block diagram of the controllable canonical form, that is when both numerator and denominator has been involved. Now we will find that in this case order is 3. So how many integrators are used? There are 3 integrators are used. So we will draw 3 integrators. So we have, this is integrator 1, this is integrator 2, and this is integrator 3. So we write variable as x1, this is one integrator, this is another integrator, and this is another integrator. So here x1 is one variable. So how we got x1? That is the integration x1 dot, because of this we got x1. So we write this as x2, then here we write x2 dot equal to x3, and there we write this as x3 dot. Now here another summation block, and here this is. So last time what we have seen, you can see, so here the elements of A2, A1, A0 has been involved, that is particularly is concerned with this x3 dot equals to A0, A1, A2, x3 1, that is x3 dot equals to A0 x1, A1 x2 and A2 x3. So here this we have to show here. So how will you show? How will you show it? So here we write here this one as minus A2, connect like this, then we will write like this here minus A2 minus A1, then here we write minus A0, this is x1, and this is u. So this is the block diagram of only denominator, but here the numerator is involved. So we have to write the output y, this we have to write, that is b0 b3 a0 into x1, b1 b3 a1 into x2, b2 b3 into a2 x3 here in this simulation diagram. So I will write down here the first part here x1. So we write down here b3 b0 minus b3 into a0 this is y. Now here another variable will come, that is from x1 dot equals to x2, b1 minus b3 into a1, we can connect here, and another is x2 dot, b2 minus b3 into a2, connect here, and lastly we have from element u we have got b3. So we can connect here b3, and it will come and it will come across it. So you will find that here that equations of y plus here b3u. So all this portion has been shown here. This is the portion, this one, this portion, this portion, and this is u portion. So this is simulating diagram or block diagram, and we can show it again, see it again clearly. So you will see here y elements of x1, x1 dot, x2 dot, x3 dot, say all the elements are shown a2, a1, a0, u, b3 and all this has been shown. Now we will take a numerical example. So here we will take one example as g of s equal to 2s cube plus s square plus 7s plus 2 divided by s cube plus 15s square plus 62s plus 48. This is example. So earlier what transfer position we have taken? Like this a0, a1, a2, b0, b1, b2, b3. Therefore we write the elements like this. So we have b0 equal to 2, b1 equal to 7, b2 equals to 1 and b3 equals to 2, and here we write a0 equals to 48, a1 equals to 62, a2 equals to 15. Now we want to write down the state space model. So how will write the state space model for this? X dot equals to, we write 0 1 0 and about this we write 0 0 1 and about the third row we write minus 48 minus 62 minus 15 into x1 x2 plus x3 plus we have to write here the other elements like this. Now we first of all we will take care of the y only. Now in this case y, what is y? Y equal to, we write down what is the y formula for y, just here b3 b0 minus b3 into a0, b1 b3 into a1, b2 b3 into a2. So this we can write down here. So y equals to 2 minus 2 into 48, second elements 7 minus 2 into 62 and third element we write at 1 minus 2 into 15. So first, second, third. So what we write y we will get as minus 94 minus 117 minus 29 and here this is x1 x2 x3 plus b0 is 2, this one 2, so 2 into u and here we write 0 0 0 1. So this is the, we can say, the state space model of a system in a controllable canonical form, and it is called extended because here we have taken care of the zeros. And suppose if there is strictly proper transfer function and this part is not there, you simply write the output as 271 only. Now these are some references: Ashish Tiwari, then D. Roy Chaudhary, Nice, Ogata. Thank you.